This question is asking us to implement the trapezium rule to integrate this function. Some functions you can't actually integrate exactly, and therefore you have to do it numerically. And the trapezium rule is one such example of doing this. One of them most basic, to be fair, but it's still effective. So I'm just going to do a little recap on roughly where it comes from. We've got some sort of function, and basically we're going to split it into different sections, all of equal width I should add. And let's say I wanted to integrate the curve under here, then I would find the area of these trapezia. And so I just sort of connect, they look like rectangles, but when you get to here, you can see that there's an increase in height. And so you're going to get a very good approximation if you work out the area of each of these trapezia, or trapeziums. There's going to be a small error. For example, there's a little gap here. And part two is going to talk about how you could increase the accuracy. Now, what you get ultimately is this formula. So for example, this is x0, your first value of x, and then x1, and so on up to your final value, which for me is going to be 1, 2, 3, 4, 5, or whatever, but xn in general. If I carried it on, then my last one would be, say, here, and then this would be xn. Get all this area. And I'm not going to talk about loads about where this formula comes from. It's quite interesting to see where it comes from. But basically, you can see that we're only going to, when we find the area of the trapezia, it's the parallel sides added together, and then you multiply by the height. So that's kind of where the h comes from when you factorize it out. And then this trapezia on the left is only, we're only going to count the x naught once, and the same with the very last one. Whereas, for example, x1 is going to be counted with the trapezium to the left of it and to the right of it. So that's why you sort of double up, and then you end up finding these heights, and that's what the y values are. So this would be y0, for example, and this would be y5, etc. Overall, though, this is really a situation where you just have to carefully put things into a table. So we're asked to use 4 strips, actually. We're already told that. Um, so n is 4. And then we're even told the width, but even if you weren't told the width, then h would be b minus a. Now that is your furthermost point minus your first 2 minus 0, 4 strips over 4. So that's where the 0.5 comes from. And then we're going to basically tabulate some different values of x naught up to, in this case, it is going to be it's going to be x4, isn't it, actually? So it's going to be 5 x values. So 0, 0.5, 1, 1.5, and 2. Okay, just increasing by 0.5 every time until you get to the very end one. And then y is the value of the function. So that's going to be our e to the x squared. Now you could write this down in decimals, but in this case, because we're using e, I think it's actually best just to leave our answers for y in terms of e. So e to the 0, which is actually 1. You could just write e to the 0, and then it's going to be e to the 0.5 squared. I'm going to leave it like that. E to the 1 squared, which is actually just e to the 1, or in fact just e. Then e to the 1.5 squared, and e to the 2 squared, or e to the 4, I could even write it as. And I'm not going to work these out or anything, I've just got them there ready to use. So then my integral to 0 e to the x squared dx is going to equal a half times h, which is 0.5, curly brackets, and I've got y naught, that's going to be 1, plus yn, which for me, because n is 4, is going to be y4, and then this is going to end up being y3, so it's going to be e to the 4, and we're going to plus 2 times all the rest of them. Okay, there we have it. So just need to carefully put it in our calculator now. A half is just 0.5, so it's going to be 0.5 times 0.5, big bracket, and then it's Shift Lun to get E. That's just E to the 1. We close the bracket on the 2, close the bracket on the main thing, and we get 20.6445. Okay, so that is an estimate for our integral. Remember, like I said, because there will be little gaps missing, and we'll round it to 3 significant figures. It tells us to do that, so 20.6. Okay, nice one. Part 2, explain how the trapezium rule could be used to obtain a more accurate estimate. Well, we could use a higher value of n. So something like that. I'm going to write increase the number of trapezia. Number of trapezia used, or used over the interval. Okay, well done.